Okay, so this is one of the inclined plane questions in this set. Let me do this one. There's like two more of these questions, but let me do each one from scratch. So by from scratch, what I mean is I'm gonna start by reciting or repeating the standard strategy, and you have many other videos of me spelling out the standard strategy. And really, this is our recommended way you approach these force problems. You start by drawing free body diagram. Then you define coordinate axis. And when you are defining coordinate axis, you pay attention to the acceleration so that, let's say, plus x direction is parallel to acceleration. And the purpose of defining coordinate axis is so that you can break forces into components. You can't break forces into components until you have access to break them into. And the reason for going through all these steps is really so that you can do step number step number 4. Write down Newton's second law equations. And so I'm writing this as a vector equation. For two-dimensional questions like this one, you need one equation per each axis. So I'll be writing down two equations, one for x, one for y. It's possible that I don't need the equation for y direction, but let me just go through the whole standard strategy from beginning to the end. So let's just start with the free body diagram. The question says, maybe I should have sketched this first. Let me just do a quick sketch to make sure I don't forget anything. There's a ramp. There's a piano on that ramp. That has some mass. And there's some applied force that's acting parallel to the ramp. And I'm given the angle of the ramp. Okay. So with that info in mind, I'm going to draw my free body diagram of this piano. I like to start out with the forces that I know have to be there. So one force is the applied force, but I think just drawing them is going to be a bit deceptive, because I ask myself the question, did I draw all the forces? And here it's really easy to be deceived into thinking, oh yeah, that's the direction of acceleration, that's my applied force, great, all the forces. Don't do that. Make sure you draw gravity. It's something on Earth, so there should have been gravity, mg. And drawing the gravity allows you to realize that it can't be just gravity and the applied force, because then that force goes in kind of this direction, and that's just nonsense. So you need the additional forces, and hopefully by now you have seen enough examples to realize the force you need is the normal force, perpendicular to this surface that you have the inclined angle of. So you need the normal force, and with these three forces you can basically make acceleration go in whichever direction you want. And it's at this point where, when you ask yourself the question, did I draw all the forces? Probably. Make sure you accounted for everything that's touching the piano. So in accounting for normal forces here, I accounted for this surface of contact. Now, does it say there's a friction? There's no mention of friction, so I think I'm just gonna assume that friction is negligible. Might not be, but in any case, I'm not given any information to use, so I'm going to be assuming negligible friction. And that's really what we do most of the time. Whenever we can neglect friction, we neglect it. And when we can't, then obviously we can't. So I did the step number 1. I drew a free body diagram. Let me define coordinate axis. So I start by recognizing my direction. Now the acceleration might not be up the ramp, it could be down the ramp, although the question text makes me think it should be up the ramp. In any case, so that should be my direction of axis. So let me define my x-axis this way, and the y-axis perpendicular to it. And the purpose of defining axis this way is so that later on, when I look at the acceleration along the y direction, I can say that's a 0. It simplifies some of my equations. And to break force into components, it looks like the applied force and normal force are already along x and y directions. So I only need to have to worry about mg. And for mg, let me just move this label out a little bit so that I have more room to write stuff. Let me just write mg here. So I can I like to start by drawing a right triangle that has the legs of the right triangle going along the axis. So along the y-axis, along the x-axis, or parallel to the x-axis. So this is gonna be my, the y component, and this is gonna be my x component. They both should have this hypotenuse mg times one of the trig functions, either sine or cosine. And to figure out which one it should it be sine or cosine, you need to track the angle that's given into this right triangle. I'm given this angle theta. So there's different ways you can go about it. Here, I guess one way to do it is I recognize this other right triangle. So then I know this angle must be 90 degrees minus theta. Then this angle being 90 degrees minus that angle, this angle must be theta. So once I track theta to one of these two angles, then I know, oh, this is the opposite side, so this should be mg sine theta from so ka toa, or so and ka. I don't need to use toa this time. Sine is opposite over hypotenuse. And this is the adjacent side, so this should be mg cosine theta. So that's my step number 3. I broke force into components once that I have to. Finally, so when you get to step number 4, if you've been following steps number 1 through 3 carefully, you should basically have all the information you need in this annotated free body diagram. You just the step number 4 is a matter of simply reading off the information that's there. So you just read off, okay, I'm gonna write down my net force along the x direction. That's going to be so I have the applied force in the same direction as the labeled acceleration direction. So apply the force, and then I have the x component of gravity, that's the opposite direction, minus mg sine theta. That's equal to mass times acceleration in the x direction, which here happens to be the entirety of acceleration. That's really the reason we do step number 2 the way we do. And net force along the y direction is equal to the normal force minus the y component of gravity, mg cosine theta, and the way we define the axis, this should be 0. And if there was a friction, I might have done something with this, but since there's no friction, the question isn't asking for the normal force. I'm basically not gonna do anything with the second equation. It's a valid equation, I just don't need it. So I'm just gonna work with this first equation, which will, I think, give me acceleration that they are asking for. So let's solve this for acceleration. Acceleration is equal to the net force that I think have all the numbers for, divided by mass, which I think I have a number for. Yeah, so let me just plug the numbers into my calculator, Wolfram Alpha, and do it that way. Let me just put everything in basic SI units. That way I don't have to deal with the units. So apply the force, 1680 Newton, basic SI unit, minus mass, 300 kilogram times g, 9.8. If I'm not plugging in units, I can't do lookup of physical constants using Wolfram Alpha, because that'll come into its own unit, and it's all or nothing. Either put units for everything or for none of them. So times the sine of 17 degrees. Degrees not a real unit. I think this is going to be fine. All of that divided by the mass of the piano, 300 kilogram. Yeah, this is one of the reasons I wanted to use this. I can just click on this to copy to clipboard. Now, when you do it this way, so it'll grade it as correct, but I don't recommend submitting your answers like this, mainly on the basis that it looks unprofessional, like rounded, 3 significant figures, great, looks professional, and it'll never give you a wrong answer through rounding errors. Oh, I don't know why it's doing that. The question might be coded with too high precision. Then keep 4 significant figures. 4 is fine, that doesn't look unprofessional. But let me make a note to myself to make a report to the author. Report to author regarding sig figs. Because the other author has been using 1% tolerance. For him to suddenly shift to 0.1% tolerance makes no sense. But round it. Don't put in all the numbers, even though, you know, that actually does maximize your chance of getting your answer graded as correct. But it's you know, it's like doing free throw underhand. Like no professional basketball player does that, because that looks so unprofessional. Like putting all the numbers in, even though it'll maximize your chance of getting it graded as correct, looks so unprofessional. So just I would say, you know, don't do it for appearance's sake. What is the velocity of the piano when it reaches the top if the ramp is 4.0 meter long and the piano starts from rest? So this is one of those where sometimes we sneak in kinematics questions as a part of a force question. So let me just do this quickly. I'm going to use the V squared formula, which says V final squared is equal to V initial squared plus 2 times acceleration times delta x. And if acceleration and delta x are in the same direction, then this product is going to be positive. And yeah, I think I can just use it as it is and basically just take the square root of the whole thing to get the V final. So let me do it that way. So the number I have here is already the acceleration, which I'll be using. So V initial squared, that's 0. So 0 plus 2 times the acceleration, that's this entire number, times the delta x. Let me do it as 4 meters. Again, I'm chosen to not put in any units, just basic SI units, numbers in basic SI units. Square root of the whole thing. That should give me 4.6, and let me keep 4 significant figures. 4.677. 4.677. That should be graded as correct. Yeah. So, and if I had to guess, if you round it to 3 significant figures for this question, I don't know. Let me. Well, then could have been within 1% tolerance. I mean, 0.1% tolerance. So if I misround it to here, then that will be great. Yeah, because I think the author accidentally used the 0.1% tolerance rather than 1% tolerance that most of us physicists use.